At this point, it's a pleasure to introduce Corey McCormack, who's with SOM. Corey, this is our last presentation before we break and head up for the Q&A. Corey is an associate principal and technical architect at SOM's New York office. His work focuses on large-scale adaptive reuse and repositioning projects in New York City. Corey is also on the New York Passive House Board of Directors, which we're very proud of. So Corey will introduce the SOM team that will present the work that they're doing.
Thank you, Buck. So today our presentation is called The Whole Carbon Picture. At SOM, we have a focus on incorporating decarbonization into all phases of our design and delivery of projects. Today, we will be sharing with you 3 of those specific efforts ongoing at SOM. The first, De-Spec, is an effort examining the SOM Master Specification to evaluate ways to decarbonize and de-chemicalize the specified materials and systems we use in our projects. Next, Urban Sequoia brings together different strands of sustainable thinking, the latest innovations and emerging technologies, and reimagines them at the scale of a building. And lastly, a partnership with Prometheus Materials to design a zero carbon building material. It's a new bio-based alternative to cement that could achieve net zero emissions in the building sector. So I'm introducing the presenters for today. The first up will be Rowan and Cynthia. Rowan is a specifications writer in our New York office, and Cynthia, specifications writer in our DC office, and they'll be talking about the De-Spec effort. Yasmin will be presenting virtually, and she is a design principal in the New York office presenting Urban Sequoia. And also virtually, Lauren is the president, CEO, and co-founder at Prometheus Materials and be presenting the same. So I'm going to ask Rowan and Cynthia to come up to present De-Spec.
So in introducing De-Specs, we've already heard a lot of the terms and concepts repeated that we'll be talking about as well. And I just hope that emphasizes the importance to all of you to, to keep this in the forefront of your mind. We've heard about the passive house and everybody's objective to get all the way over there to zero carbon buildings. And so on top of passive house, we're going to be talking about reducing embodied carbon in the buildings. So as Corey mentioned, we are decarbonizing and de-chemicalizing our projects. And as a result, our specification masters rather, and as a result, that went to de-specifying, which we are fondly referring to as De-Specs in the office as we work through updating our masters. And it was funny, as we started this process, everybody kept referring to it as De-Specs. And finally, we were like, well, this is really just updating our specs. It's not something special anymore. This is becoming the norm. This is the way we are going to be doing our practice. And so you can see it's reducing the carbon emissions in the materials we use, looking at the materials and reducing the amount of chemicals that are going into our buildings. So there's 3 objectives here. One is to understand. One is about implementation, how we're implementing. And third is identifying some tools that we've been using. So understand the importance and opportunities for meaningful carbon and chemical reductions in the architectural materials and products. As we heard today, for a while, we've been looking at operational carbon. That is the total from all the energy sources to keep the buildings that we are occupying, to keep them warm, to keep them cool, to keep them ventilated, lighted, and powered. So we've achieved a level of success with improved and high efficiency HVAC systems. We are using LED lighting, Energy Star appliances, and solar energy. And at SOM, we decided it's time to move beyond that. So we really took it upon ourselves to do some serious studies in-house about the embodied carbon. We pulled together over 50 of our colleagues representing many different disciplines around the firm. So we had perspectives from structural, from MEP, from just architectural as well. And we're focusing, like I said, upfront embodied carbon and then end of life embodied carbon as well. So how are we doing that? We're starting with using less material, sourcing responsibly, build for life or longevity, reuse what exists, and then thinking circular. And this, and so in starting our research, we found this on Building Green that 70% of a building, that the carbon factors into 73% of a building. And so, we asked ourselves, what do we want to know? We want to know where the embodied carbon hotspots are. What are the most chemically intense materials and surfaces that we have in our buildings? And which materials can we change, revise, take action on to create a healthier environment? And the results are reflected here. So a good over 50% of the embodied carbon in the buildings, as we've been hearing, is in the concrete and steel. So in the substructure and the superstructure of the building, followed by enclosure and then interiors materials. And then somebody was saying earlier, talk early in your projects. And so I'm going to emphasize that as talk early and talk often. We can make the biggest impact in the design and planning stages. When we are setting our goals and objectives for a project from a design perspective and looking at the owner's priorities in a building, that's where we have to decide that reducing embodied carbon in our building is equally as important as those goals. And so again, it becomes a guiding principle in designing. Clearly, we can do nothing, and we're just saving ourselves the trouble and any carbon by just letting the building exist as it is. But we know that's not usually possible. So the second option would be to build less. And so we're hearing great stories about renovation and adaptation. And so you're maximizing an existing building's assets and moving forward with that. The third, when you get around to 50% of the, beginning of construction, you can build clever. And so this, choosing low carbon materials to meet design objectives, considering location where materials are manufactured and then bringing them to the site. Next, you can build efficiently, again, using new technologies, having the contractor choose to find materials that are locally available, relatively speaking. And so then what was our objective in all of this? We decided we wanted to create transparency. We wanted to define and achieve, not archive, achieve sustainability targets on our projects, and then prioritize systems and materials as we learned more about what there was, as we learned more about the materials and their impact on buildings. Rowan's going to take over.
So how do we target transparency? Step one, we identify all the standards and certifications that govern transparency. These are pretty standard across the industry. We all know what these bodies are and what they represent. Secondly, identify the product databases that have all of the EPDs, HPDs, et cetera, in our specs. And then update the specs, starting with the most impactful for human contact and mass of buildings. So in implementing a practical approach to addressing embodied carbon and chemical reductions while maintaining expected performance, I'm going to walk through a few strategies that we've implemented in our master specifications. But I just want to reiterate, and I think Cynthia was quite modest in how she described the process. It took almost 3 years across the entire firm. We're a global practice with offices over the world. And so we all came together and collectively were a part of this research effort, and we're pleased to present to this group and to others as we've done in the past. These are the divisions in the specifications that we focused on. Again, the really important superstructure divisions, as well as the high touch and high use choices here. So what has changed in our specification masters? Well, up front in part 1, for those of you who are familiar with CSI master format, and it's divided into 3 parts. In part 1, what we've done was we've addressed submittals, making declarations a part of the submittal process, whether or not the project is pursuing LEED. A lot of times we get pushback saying, well, if we're not pursuing LEED, why is this important? And we took the approach during our deliberations that why don't we push the industry in saying this is a project requirement, not a LEED requirement. And so that was really the turning point in our deliberations as to how we can really make a meaningful impact as far as embodied carbon goes. In part 2, obviously addressing the sustainability characteristics. What we did here specifically is listing things like global warming potential in the spec, the target. Basically, this is where we want you to be in terms of what the GWP is for a particular material or product, listing that in the spec, again, as a product requirement, not necessarily a LEED requirement. And then, of course, favoring the suppliers and manufacturers who already have or can achieve these requirements, pushing the envelope, pushing the boundaries of what is industry standard for recycled content, biodegradable content, et cetera, so that we are addressing the need for clean energy sources for manufacturing processes. This does not happen in a vacuum. We take into consideration qualitative and quantitative analyses, and selecting materials that are built to last. Since you talked about durability, some of our other colleagues, esteemed colleagues on the panel, have also talked about longevity, the long life, the durability of materials and systems. That's important. Obviously, prioritizing natural materials. We've heard a lot about bio-based materials, which is the next iteration, but the appropriate use of natural materials as opposed to synthetic materials, we believe, is strong in terms of the embodied carbon. And engaging manufacturers in the design assist process to optimize usage. Quantitatively, we all know that less is more, and so we are pushing our design teams to reduce sizes, reduce complexities, work within manufacturers given modules, et cetera, and employ prefabrication to the greatest extent possible, reusing through recycled content or repurposing. And just minimizing and simplifying our material usage for things like facade panels, optimizing thermal performance by climate zone, and obviously using the low carbon materials that we have available to us. We'll talk later on in Yasmin's presentation about some advancements where that's concerned. I want to spend a little bit of time talking about facades and what we've been doing. This is another snapshot of our embodied carbon tool that we've developed in-house, where we are taking a look at where are the carbon hotspots in terms of the facades. And the big glaring one is the actual facade mullions. As we might be familiar with in this room, at least, aluminum is bad. I mean, there's no way to sugarcoat it. It's a great material in terms of its durability, its ability to in terms of efficiency. It's a very lightweight material for what it can handle for a facade. But in terms of embodied carbon, it's the chief offender here in this discussion. These figures are taken directly from the inventory of carbon and energy, the ICE database. And again, we are extrapolating this information. We are comparing it with commonly available EPDs, what's in there in terms of the global warming potential, and then putting that target literally in the specification as what the submittal should match. As I said, it's the largest contributor to CO2 emissions in all of the industries, one of the most energy intensive materials that is actually produced. Glass, even though it's lower than aluminum, the volume of glass that's used in our facades obviously is way more than the aluminum. And so this ends up being a very high number as well. Precast concrete is another facade choice. And what we're seeing is a shift towards, in the industry, more use of materials like wood, and where we have opportunities for carbon sequestration. If we compare aluminum to other metals, you can see the difference here. Speaking of metals, in terms of structural steel, very high carbon emissions as well. So the talking point here is really about, as we're saying, putting in the specification what we expect to be target recycled content for all of the steel, in addition to what we expect to see for the global warming potential.
Okay, and we'll take a minute and talk about stone as well. This is a natural material, as Rowan was saying. Want to be using more natural materials. However, lowering the embodied carbon with stone isn't necessarily a part of the actual material. And so this then gives us an opportunity to really work more with the design team about how they're using the stone. So this is less technical and more about design. Excuse me. We're encouraging and working with them to reduce the quantity and thickness of the stone, as Rowan said, reducing complexity. If slabs, are coming in at 6 by 8, can we use 6 by 8 instead of 5 by 7? And so we're having more conversations like that quite early in the stages of the design presentations and with our teams. We're encouraging our design teams to choose stone that's fairly local or regional anyway. Reduce the distance from the travel distance from the quarry to the processing location, and the processing location then to the project itself. Specify low VOC fillers or sealers, or maybe none at all, depending on the stone and the purpose, the functionality in the building. Minimize the finishing as well, and sustainability considerations for quarries. So what that might mean is, are they using water recycling at the quarries? There's a lot of water that goes into cutting stone. Are they using higher efficient machinery? Do they maximize efficiency of quarrying by reusing the waste? And then also in talking with the design teams about the softer stones. As softer stones, again, depending on how it's being used, require much less energy to extract and to cut. We've talked about adaptive reuse and renovation here today. And so in that, we're just, ideas. We recycle bottles. Why can't recycle buildings? We looked at how having conversations very early in the design stages was really important, that maybe we can reuse the assets of the building. And according to Architecture 2030, 2/3 of the building stock that will be used in 2040 are already around the area and in existence. And so we need to get creative about how we can update some of these to continue for another 40, 50, 70, 100 years. And so one example of a recent renovation that we have is Lever House, which I'm sure many of you are familiar with. And so then the third part today is about identifying and implementing specific tools that we've used to improve, decarbonize, and de-chemicalize project specifications. So we are fortunate to have a sizable sustainable engineering studio and digital design studio as well. And so we've been able to develop a number of tools. But this is just a little public service announcement to define the EPD and HPD. Again, we're all, this group here is quite familiar with what those are, so I'll skip over that. One of the tools that we have access to are these design guides that were developed in-house. And so they're not developed for all the materials, but for the materials that we do have, concrete, tile, stone, steel, are informative on the left-hand column. There are just general information and questions to ask yourself. And on the right-hand column, it's talking more about the impact on the environment. And so as designers, we can be more well-informed as we're making decisions. We've developed a tool called Embodied Carbon 101, whereby people can input data of what materials they have in a project and the quantities, and that will inform us with what percentages by discipline we have in the building for embodied carbon. And then by the push of another button, we can look at the architectural assembly and see where the embodied carbon is with that as well. So we've, as Rowan said, we've been doing this for many years, probably 3 to 4 years, and I'm sure some of it started before that. And so these are some projects that recently have either been completed and occupied, under construction, or still in design. And so with each one, of course, we're learning something better to do on the next one. And we are really encouraging the industry to take action. As Rowan said, we spoke about this earlier last month at a CSI conference, and really encouraging people to think about all the principles that are being presented here today. Try to build with less material, understand material dimensions to reduce waste, avoid, this is what we've always done, and try to think creatively about new ways to go about reducing carbon and chemicals in our built environment. Utilize alternate design strategies, renovate, reuse, refurbish, deconstruct, and then utilize the databases that we're all familiar with and that Rowan put up to do research on your materials.
Yeah, I mean, everything that we've presented here is stuff that we can and should be doing. We look to our industry partners, both in manufacturing as well as the builders, to partner with us, as well as owners, obviously, to partner with us. So everything that we have shown here can already be done. And now we'll hear from Yasmin, who will talk about what we feel is next. And with that, we'll introduce Yasmin, who will talk about Urban Sequoia.
Hi, everyone. Can you hear me?
Yes, we can.
Yes.
Perfect. Great. And I apologize for not being able to be there, but thank you again for inviting me today. So maybe following from what Cynthia said, should we be doing things because that's how we always did it? Or should we be putting a different perspective on, to look at things through a different lens? Is the provocation that we brought on ourselves in this project that I'm going to show you now. So let's hope that you're going to be able to see my slide. How does this look? Can you see my screen? Yeah, yes. I can see it on your screen. Fantastic. Okay, so Urban Sequoia is a concept that we propose, is a prototype actually we proposed because we asked ourselves, how can we think about buildings differently? And can the buildings be a solution to the climate problem instead of maybe contributing to some of the challenges? And when we looked at this equation, stepping out for a second, cities account for about 70% of world's carbon emissions. And this is not just buildings, the industry around the cities too. But surely buildings contribute to a huge number when we look at the cities. So we said, Well, net zero architecture is fantastic. And I'm sure all of us in this room is doing a lot of great work to go there. And we saw some of my colleagues actually work that we're doing. But can we actually think about a scenario where net zero architecture is just not enough? And can we think of buildings that act like trees? Can they breathe in carbon from the atmosphere? So we came up with this proposal and we said, well, is there a way to absorb carbon from the atmosphere through our buildings? And there was born Urban Sequoia that was presented at COP26. And what this does actually, it looks at leveraging existing technologies and emerging solutions that exist elsewhere, either in our industry or elsewhere in other industries that they haven't quite made their way into the building industry. So, and we looked at, okay, if we were to try to do this, what type of scale would we look at? So while every type of building, every scale requires a unique, different size, different type of intervention, from these three different typologies we're looking at, which are the most common in many cities, a high rise, we know that high rise is the most challenging probably to even get to zero. So we said, okay, well, let's take the most challenging one and let's see what we can do to this. And through a lot of research and collaboration with the industry, with our peers, with advice from individuals like Ed Mazria, Will Schrubar, we try to dissect how are we going to address a high rise that absorbs carbon from the atmosphere. And some of the technologies I'm going to talk about, you're going to hear from Lauren after me also. But the first step for this was actually to look at modularity and prefabrication. So let's look at actually what we have in hand first, before we start to include leveraging technology that exists elsewhere. Probably many of us also in this room knows that by going to a modular system, by prefabrication of many parts of the building, we can reduce actually the carbon of our building significantly and also avoid waste significantly as well. And with holistic integration of components, by that we mean structure, MEP, and the rest of the systems in the building, we know that we can go to approximately 60% carbon reduction upfront. But clearly 60% is not going to be enough. So when we talk about something that absorbs carbon from the atmosphere, we have to look elsewhere. So we did some research on what could this mean? And we know that there's biomaterials that exist. We know there are nature-based solutions like microalgae, and there's technological advancements like direct air capture systems, different technologies that exist in this realm. So we asked ourselves, can we use some of these innovative technologies, and how far can we push it? So I'm going to give you a snapshot of this before I explain further. So this is what we found. So by doing all of these things, we were able to reduce the upfront carbon of materials by about 95%. And over 60 years, we think that the building could actually absorb 350% carbon than emitting 100% in a typical building. So what would this take? What do we need to do for this? What are the types of materials or systems that we can explore in buildings? So the first one, I'm going to talk a little bit about biomaterials. For example, here we are actually talking about BioBrick, and Lauren is going to talk a little bit about the bio cement that we're collaborating together on. But it's very simple ingredients. It's aggregate. It has aggregate in it. It has microalgae in it, and it has a water solution, it's a hydrogel solution that goes in it, which helps us then cure the biomaterials that we're talking about, for example. And this is not the only one, but this is the one that I like to show today. And the amazing thing about this is actually it can be locally sourced mostly, and because the content comes from fairly basic things, the potential of it for being applicable in different parts of the world is amazing. And this is some samples that we actually produced back in the day when we were preparing for this Urban Sequoia presentation. And what could this do to us? For example, we should be able to replace part of the building structure, internal wall elements and insulation with things like biocrete, which I just talked about, BioBrick, bioplastics. And this could mean that actually over the lifespan of the building, some of this continues to absorb carbon, but also significantly reduced embodied carbon upfront too. And yes, these materials are not commonly used in our industry at the moment. But again, our provocation was like, can we one day, how can we imagine a world where we do? And the second part that we looked at was what we call the nature-based solutions. So this is what you see on the picture. Actually, it was a building facade developed by, built in actually Germany and developed by Arab. What it works on a very simple premise is photosynthesis. So it takes microalgae, adds sun to it, and basically carbon absorbed, and produces more microalgae in the system. So can we think about, and often we will try to reduce solar gains in our buildings, for example. We will try to minimize some of the facade areas sometimes. And if you think about it the other way around, how can we optimize and maximize some of these things? Can we actually think of a world where parts of our facades could be used for microalgae production, for example? And what's amazing about microalgae is, for example, this is a farm that exists already. The algae produced here is being used as a source of biofuel. So can you imagine a world where the building produces its own source of fuel? How amazing would that be, rather than rely on fossil fuels, as many of the buildings that we live or work in today do. And what this could mean, actually, we can integrate this on the facade, let's say, and the microalgae produced here could be used as biofuel, as part of heating systems of the building, but also in other industries as fuel or as bioprotein sources as well. So how can we think of maybe different uses of this, and how can we integrate nature-based solutions to our buildings? And this is the example of the building that I mentioned to you earlier, designed by Arab, Solar Leaf in Hamburg, actually takes this approach. So the facade that you see here are producing algae similarly. And the last system that I want to talk about is technological advancements. You know, back in the day, I don't know if you remember this, but I guess it must have been about 15, 20 years ago, when the photovoltaics were advancing. They used to exist in a farm format. So they used to be in open air fields in a large farm areas, and producing a lot of energy. So right now, what you see on the screen is a direct air capture farm. So these machines you're seeing on the screen are actually capturing carbon. So the way it works actually is collects the carbon, and it potentially produces a commodity out of carbon that could be used in many different areas. And also it could be used as industrial material for building industry also. So the way it works is air flows into the machine, either naturally or through a fan. And the carbon is collected through a filter. And then there's different ways of either by, let's say, temperature swing or moisture swing or electro swing, the carbon is then released and bottled to be used as a commodity. So is there a way that we can imagine a building that actually does this too? And what's great about our buildings, we have a natural stack effect often in our buildings that many of us would try to limit or reduce. Can we use some of the building systems or building physics like this to incorporate carbon capture system into our buildings? So can every building literally absorb carbon from the atmosphere? And what could be amazing about this is, again, the carbon absorbed could be used as building materials, such as carbon fiber, for example. It's already being used in beverage industry, and it can also enhance farming. And there are various sources, other sources that could be added to this list as well. But hopefully this shows the potential of maybe thinking a bit outside the box in our industry, and dreaming a little bit too, what the future might be like. And interesting quote from our Secretary of Energy. So in COP26, a couple of days after we presented, she actually also highlighted direct air capture technology as one that our government is investing in significantly. And that they're gonna continue to invest in, and they see this as one of the solutions for the future, which was quite exciting actually too. So in summary, our building uses some of these systems that I talked about, some of these innovative technologies that exist elsewhere in other industries, and brings them to combines them into the systems of our buildings. And as a result, we think that we can, by doing these, we can reduce the upfront carbon by 95%, and over 6 years, absorb 350% more carbon than a typical building would have emitted, actually. And I don't want to portray that this is a building problem only. I think we need to think about our buildings holistically and our city districts and cities together too. So while a building can make a difference, as we've shown today, a collection of them makes even a bigger difference. So when we think of this as a network of buildings in a district, in a city, their impact gets amplified further. Can we potentially think of the biofuel produced here to be used in other industries? Can we think of a network of CO2 actually through our cities? For example, is our gas lines, are they going to turn into a different, maybe carbon line one day? Who knows? But surely, if you think of this in the district scale, the impact of it is going to grow significantly. And we can imagine a scenario where the biofuel as well as the carbon collected and produced in our building could be used in other industries such as building materials, or in food and beverage, or in agriculture as fertilizer, or in freight as biofuel, or energy again as biofuel. And it could be quite amazing. And we're imagining that actually our cities could have the potential to become network of these systems if they were to connect together and if they create a network holistically together. And if you think of the global scale, what would happen? Can you imagine if all of our cities took a similar approach? In the cities, can the buildings become part of the solution to climate challenge rather than maybe contributors to climate challenge? So that's the provocation we asked. And if we were to do this, we could save 1.6 billion tons of carbon every year. Maybe not the full solution to our climate challenge, but surely a big one. So finally, I'm going to stop this for a second and I'm going to share it again to be able to show you our video as well. Just so hang with me for a second. So we presented a video also that summarized some of these ideas, and hopefully this is going to work. All right. Are you able to see my screen again? Yes. Perfect. Thank you for your time. And I will just give one little clue here. So next week, there's COP27 coming up again, and we will be presenting a new version that is called From Concept to Reality. It will be on the 8th. If you have time, please join us for that presentation too. And I think I have Lauren here. Lauren, are you with us?
Yes, I am.
Perfect. So I think I prepared it really well for you to talk about the BioBrick and BioCement. So I'm going to pass the word to you and let you introduce as well.
You did indeed, Yasmin. Thank you very much. And hopefully everybody can hear me. Well, I appreciate the opportunity to speak to the group here today. And let me just share my screen here. So our company is Prometheus Materials, and we have developed and are producing an ultra-low carbon alternative material to concrete. We say ultra-low now. We'll be at 0 carbon within the next 6 months. And then we have a clear path to carbon negative, which is the ultimate goal. So the problem we're addressing is huge. The concrete problem is massive. As I'm sure you're aware, concrete is the second most used material on Earth, second only to water. It's responsible for 8% of the Earth's annual CO2 emissions. And it also uses about 9% of industrial water production on an annual basis. So the problem is very, very large and very dirty from a climate perspective. But as Yasmin mentioned a little bit ago, the problem is actually worse than that, in that building stock is forecasted to double between now and 2060. And you've probably heard this statistic before, but that's the equivalent of building a new New York City every month for the next 37 years. So our solution to that is we use algae to produce an ultra-low carbon alternative to concrete. So it's important to keep in mind, this is not concrete. This is not Portland cement or Portland cement-based concrete. This is a completely different material that has many of the characteristics and capabilities and sometimes exceeds the capabilities of current concrete. So we're combining sand or algae. We're causing it to go through a process called biomineralization, which I'll talk about on the next slide. We combine that then with a hydrogel and sand, mostly sand, to produce CMUs, bio-CMUs, which you see here on the right. So the same characteristics as current CMUs, only extremely low carbon, heading to 0 carbon. So the biomineralization is really our secret sauce. So that's really using biology to create minerals, in our case, calcium carbonate. It's a very similar process to what nature uses to produce seashells and coral reefs. We use all natural algae, no GMO, and we stimulate biomineralization to occur on a commercially viable basis and timescale. So our bioconcrete, as compared to traditional Portland cement-based concrete, our thermal conductivity is about 90% less than Portland-based concrete. We're about 15% lighter in weight. And currently, we estimate that we have reduced about 90% of the embodied carbon in concrete, and again, heading to net zero. We go through a process of curing that's very different than what traditional concrete does. Concrete goes through a chemical reaction process that oftentimes is kind of looked at 28 days. That's frankly a somewhat of a made up number, but it's a standard that a lot of people use. We don't go through that process at all. We go through a process of dehydration. So basically we are evaporating virtually all of the water from our blocks, and that occurs over about a 7-day period. So it's much quicker. Our compressive strength is above the minimums. The minimum for an ASTM is 2000 PSI. Currently, we're around 2,400. We've had done tests that have gotten up into the 5,000s, but our blocks right now are right around 2,400. And so and as I mentioned earlier, we're basically recycling almost all of the water back to the atmosphere, whereas Portland cement-based concrete uses a tremendous amount. And it's consolidated inside the concrete for the life of the concrete. So the way this technology came to be is that the U.S. Department of Defense, DARPA, Defense Advanced Research Projects Agency, was looking for a way to see if they could use living materials, biology, to create hardened structures in the middle of the desert somewhere. They knew they couldn't fly concrete in because it's too heavy. And they also knew that they didn't want to truck it in potentially over large expanses of hostile territory. And so over a 5-year period, 4 professors from the University of Colorado came up with this process of using algae and biomineralization and a hydrogel to create basically an alternative material to concrete. And so that process was very successful. They graduated from the program with DARPA. And what they didn't initially plan on doing, but they realized afterwards, was not only had they created a replacement material for concrete, but oh, by the way, it's also virtually zero carbon. And so with that information, I joined the company, and we founded the company Prometheus about 1.5 years ago. And then this year completed a pilot demonstration project with Microsoft. And this is the group at Microsoft that's building between 50 and 100 data center campuses, I should say, worldwide on a annual basis. So our go-to-market product, which is where we are today, actually where we are today is we are in the process of going through ASTM testing and certification. Once we complete that process, then we will begin early production of our bio blocks. So you see a picture of our blocks here, both on the left and the right. We are focused initially on CMU replacements. That's initial go-to-market. That will be followed then by other precast concrete applications of all sorts, and then ultimately producing a ready mix alternative as well. So as I'm sure you're very well aware, that CMUs are used all over the world in massive quantities. Hundreds of billions per year are made and used. Heavily used in developing countries, data centers, schools, and many other buildings as well. So we chose CMUs initially because there's a low barrier to entry in terms of the process of going through testing and certification. And also it's very capital efficient. But as I mentioned earlier, we will then move on towards ultimately going into a ready mix product and the regulatory approval process for ready mix, which is significantly longer and more extensive than what it is for CMUs. So we have received our initial ASTM certification for non-structural CMUs, and now we are in the process of going through and testing for structural certification. We anticipate having that completed this quarter. So as I mentioned, we then go to precast applications as well, which we're very excited about. From wall panels, ceiling panels, trusses, any number of types of precast applications. We mentioned that initially we've gotten our sign off for non-load bearing. will then get approval for a load bearing internal as well as exterior over the next couple of months. Our focus has been to, unlike other companies that are out there working to reduce carbon in concrete. And it's funny, people will ask me about our competition, and we really don't look at anybody as competition. And I don't mean that to sound arrogant at all. What I mean by that is that this problem, concrete and CO2, is so large that it's going to take, frankly, all of us to succeed. And so we're very much hopeful that everybody that's attempting to do something will be successful. But most companies that are approaching this are working with the supply side, concrete and cement manufacturers. And we are taking a very different approach. We're working with the demand side. We believe it's building owners, designers, architects, the folks that specify materials that really will be the key for us to specify the use of our materials, which then the supply side will make and provide. So here's just a kind of a vision of the types of products that we would be making here in the midterm, which would be starting really in about another year and a half. Our model is a licensing model. So while we are initially producing blocks internally in Colorado at our pilot facility, the way that we get out there and really get this technology distributed worldwide, pardon me, and therefore really start to have an impact on CO2 emissions worldwide, which is our real goal here, is to focus on a licensing model. So our model is that we will prepare the algae. It will be spray dried, and then we can ship that. It's very light. We can ship that then anywhere in the world to manufacturers who would then use that bio plus our techniques to create biocement and bioconcrete and bioconcrete based products locally. And locally is the key for both concrete as well as CO2 reduction. And then I think this potentially is another angle of the same building that Yasmin showed earlier. But our ultimate goal here is to reduce CO2 emissions worldwide by a gigaton per year. And we believe that we have the technology as well as the market capability to be able to deliver that. We are very excited about Urban Sequoia, and we think that it's a fabulous idea and a great match with our technology and what we're doing as well. So our partners, we've had companies actually come to us. They've recognized that they either use, make, or specify the use of massive amounts of concrete, and that is just not sustainable on a going forward basis. So we're very thrilled to be working with Microsoft, GAF Roofing, SOM, and Autodesk Foundation as well, to focus on reducing CO2 in building materials in a very meaningful way. We've had a lot of press, over the good fortune of a lot of press over the last several months, and I would encourage you to take a look at some of this, and you'll get probably a much better sense of what the company is all about and where we're going. But we are very excited about what we are doing, and we are very focused on one thing and one thing only, and that is producing a zero carbon and then a carbon negative alternative material to cement and concrete. So I appreciate your time and your attention. I look forward to chatting with you afterwards.